Here's the last form of radioactive decay that we'll look at: electron capture and gamma radiation. This is another option if you have a nucleus that is unstable due to too many protons. Now, we already looked at the option of positron emission, where you could take a proton, turn it into a neutron by releasing this tiny positron particle, like a positive electron. Here's another option for getting rid of an extra proton. Electron capture means just that, where the nucleus will absorb or capture one of the atom's electrons. And now this kind of makes sense. It's usually an electron coming from the 1s orbital, because it would be an electron then that's close to the nucleus. In this case, check out this little equation. Here's my positive proton, mass of 1, positive charge. If I capture an electron, now you're going to see the electron on like the reactant side. We're adding an electron, different from that beta decay. Beta decay will produce an electron. You'll see the electron on the product side. With electron capture, you are capturing or absorbing an electron. You should see it on the reactant side. Well, this makes sense then. If I take a proton and I add an electron, I should get a neutral particle with about the same mass as a proton. Well, what do you know? It's a neutron. The proton will turn into a neutron. So the mass will stay the same, but the atomic number will decrease again by 1. We're forming a neutron, so the mass is about the same, but 1 less proton means your atomic number will go down by 1. Now, in this electron capture process, you should form a more stable nucleus. When something is more stable, it always means low energy. So in order to fall to a lower energy level, kind of like we had mentioned with electrons, you have to release any extra energy. But when we were talking about electrons jumping down the energy levels, we said the energy was released in the form of light. This is a little more serious change here. This is a change to the nucleus, not just electrons moving up and down the energy levels. So we're going to release energy similar to the electrons, but it's higher energy waves. It's not just visible light. This time we're going to release energy in the form of gamma rays. So you might kind of remember back to the electromagnetic spectrum. We had the visible light. On the top of the visible light spectrum was like the blues and the violets, the high energy colors of visible light. Beyond that would be ultraviolet light. And beyond that is when you get your X-rays and your gamma rays. So this is a really high energy wave. Its symbol is this guy. It's a Greek symbol for gamma. So that last little goofy symbol, that squiggly thing, that just means energy is released. Gamma rays are released. Oh, cool. So it's nothing that I have to worry about when I'm balancing these nuclear reactions. It just shows me that this is highly energetic. We're releasing tons of energy. It says here that gamma radiation can only be stopped by a thick sheet of lead. Gamma radiation is very penetrating. We're really forming a neutron which stays in the nucleus, so we're not really emitting any particles, but we are emitting really high energy waves. So it's going to take a pretty thick sheet of lead to stop this form of energy. As far as your health goes, it says that gamma radiation does tend to pass through most cells and tissues. But it doesn't cause severe damage. So I think about it this way. Of the different forms of radiation that we were looking at, we had the alpha particle. The alpha particle was the helium nucleus. That was the alpha particle. Then we had the beta particle, which was the negative electron. There's your beta. Your positron is very similar, but it's like a positive electron. And then here's your gamma rays. Think about it this way. Your grass on the lawn is like the cells in your tissues. That alpha particle, that's the heaviest of all the particles. It has a substantial mass, 4. Okay, so think about this being like a big rock or a big boulder. You're not going to push it very far across your grass because it's heavy. But with it being so heavy, you're probably going to damage the grass blades below it. Alpha radiation can be stopped by a piece of paper because these are big particles. It also doesn't penetrate very thick into your tissues. So you're not going to damage a lot of cells, or you're not going to damage like your internal organs, but you really can do some serious damage to like your mucous membranes. It'll damage surface cells, but it's not going to penetrate real far. Like a big boulder that you're trying to push across your lawn. You're not going to push it very far, but since it's so heavy, the particles of grass underneath are probably going to get damaged. The beta, decay, and the positron, these particles are very similar. They really don't have substantial mass. So again, it could be like rolling a little golf ball across your lawn, or maybe like a softball, where you can roll this farther than a big rock. So you could affect more blades of grass, but since these particles don't have substantial mass, you're really not going to damage them. Kind of the same thing with your cells and tissues. It's going to penetrate thicker, deeper into your tissues, but not cause severe damage. Then you get to the gamma. And again, this isn't really a particle, it's just a form of energy. Think of this as like wind. This is wind blowing across your lawn. It's going to affect every blade of grass. But again, it's not going to like squish the grass. It's not going to damage the grass. But all blades of grass will probably be affected by the wind. That's kind of how I think about gamma radiation in your cells. It's going to affect most cells. It's penetrating, which is why it doesn't get stopped until you have like a real thick sheet of lead. But you have to be pretty far away from the source to not receive any radiation. Kind of like it being wind across your lawn. All particles are going to be affected. It's a form of energy, but it shouldn't do severe damage. Now, all of this depends on the amount of exposure, the length of your time, being exposed to this type of radiation. So you'll notice people that work in radiology or around radioactive sources, they'll often wear lead coats, and they're around this every day. So over prolonged exposure, then we could start talking about some damage to our tissues. Or sometimes they'll wear these little badges. They'll record the amount of radiation that they're being exposed to. And that's something that they'd have to monitor. Visually, here's a good example of this electron capture and then gamma decay or gamma radiation. So let's get my little beryllium nucleus. Be, beryllium. It's beryllium mass 7, and I can look at a periodic table. It's element number 4. Or I could look at this picture here. There should be 4 protons, so the red must be the protons. 2, 3, 4. If the mass is 7, there must be 3 neutrons. 1, 2, 3 neutral neutrons. Excellent. Then we're going to capture an electron from that 1s orbital. So on the product side, which I guess I could write this in as plus electron, negative 1 electron. Here's my product. Lithium, 7. The mass stays the same. However, I'm taking one of those protons and turning it into a neutron. So this is going to be 3 protons. So if I check what I got here, yep, proton, 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 whoopsie, proton, positive. And then I should have 4 neutrons. So the mass stays the same. And then we would release energy. Let's do that in blue. And so this would be my symbol for the gamma radiation, which is up here. Other examples might look like this. Let's see what we got. Fill in the missing particle. I know this is gamma decay because you'll see this crazy looking symbol. That's gamma. Gamma radiation. All right, let's see what we got here. The mass should stay the same. 26 plus 0 is 26. But the atomic number is going to go down by 1. 13 minus 1 is 12. I want to look up element 12 on the periodic table. Magnesium. And then again, the gamma, that's not necessarily a particle. That's going to be a form of energy. High energy. The second one, I've got some nickel, unstable nickel. The mass stays the same at 59, but I'm going to lose a proton. So my atomic number will go down to 27. I look at the periodic table. Element 27 is cobalt. So again, this electron capture and gamma radiation, they kind of go together. I'm capturing an electron capture, and releasing the gamma decay, the gamma radiation. Now this could happen, again, like any of these decays, this could happen successive times until I finally produce a nucleus that is stable.